Are we using the same script as yesterday?
I'm actually going to, I added just a few things. So let me go ahead and resend this.
Oh, thanks.
Yeah, just a few things that I thought of today. And then that way, anyone who wasn't here yesterday can also have it. Okay. So there will be just a couple of little things that I thought might be interesting that aren't in the tutorial document that are included in there.
Oh, thank you. That's very useful.
Yeah, great.
Okay, well, so welcome everyone for the second day of the workshop on digital signal processing in R. I think there no other introduction is necessary. So Chris, floor is yours, and we can begin.
Awesome. Let me go ahead and move that over. All right. Share my screen and then immediately, hopefully change that. You should still be able to hear me. I should still be able to hear you if somebody wants to test that.
Hello.
Hey, there we go. We don't have the same problem as yesterday. Okay, good. Oh, except I don't know if I shared my audio. Let me stop share just to make sure that I do. Oh no, I do have it on. Okay, second guessing myself here. But now, let's see. Oh, let's try this again. There. Okay, should be able to see my, you should be able to see my, my RStudio? Yes. Yeah, good, awesome. Okay, cool. Yeah, welcome back, everyone. We're going to work with some higher dimensionality today. Really excited about this because so we're working with MR images, which is an area of research that is very, very near and dear to me. And we're going to be using some actual techniques that that I do use, on a real sort of research basis that I've done on a larger scale and published. So I'm happy to kind of dig into some things that that I use, more or less day to day. So I split the two parts of the workshop into what I called one-dimensional data and two-dimensional data. But I guess a good way to sort of start out talking about images is, it's really, there are multiple ways of considering dimensions, and the more you kind of actually just sit and think about it and what the data represents, I think is a good way to understand ways of tackling some of the methods for analyzing them. So in some respects, MR images can be considered two dimensions. So that's how I represented it in the tutorial document, because instead of just one dimension of, for example, amplitude, which is what we were dealing with a waveform, we have two dimensions. So we have X dimensions and, and a Y dimension in the image. In another respect, they can be considered three dimensions because for each pixel, or in this case, what we call these are voxels, because these are volume data. So each pixel represents three dimensions of information, because a slice has both horizontal and vertical dimension, but then also a depth to it. So we call these volume pixels or voxels. Each one of those has an intensity or an amplitude of its own. So in that respect, these can be considered three-dimensional data, because you have one dimension of amplitude that is represented for each pixel or voxel space in two dimensions. Another way to think about these data, because we're dealing with images that are moving over time, so we have videos, is that they're actually 4-dimensional data. So we have voxel intensity in some voxel site in a 2-dimensional array over time. And this is not to make the situation more complex by talking about it this way. This is to hopefully just get you thinking about really understanding what your data are, because the better you understand how the data are actually represented, the more you can sort of have ideas about how you can go about solving certain problems. And that's really what we're going to be looking at today, is just sort of kind of, putting some thoughts together about some of the techniques that we used yesterday, combined with some new techniques to try to solve some problem. And the particular problem that we're going to be working with today is also something that's very near and dear to me, is nasalization. So let's go ahead and start by, well, I guess re-downloading the data. So I have now kind of reset my workspace here. The only thing in the workspace is the download from Dropbox function that we had from yesterday. So I'm going to go ahead and then download that data and load it in. So now I have a new object in the workspace called MRI data. We saw this data yesterday. If we look at the summary, if you remember, we worked with not the first 2 data fields, but data 3 yesterday. So data 3 was, for those of you who are not here, data 3 is I'm sorry, this does take longer when I have Zoom going than it normally does. Oh, it shouldn't be taking this long though. Oh, I'm not really sure what happened here. Well, it's as the name implies here, we worked with this noisy scanner audio data from yesterday. Today we do have audio. We're going to listen to some of the audio, but we're not going to be doing any sort of analysis or manipulation of the audio itself. We're going to be working with the images. So let's first, I've got 2 different data sets here, and I don't know what is happening. 2 different data sets here of images, and they're related to the paper that these data are part of. And let's go ahead and just look at some representations of what these 2 data sets are. So, oh, I'm sorry. Something is definitely wrong. This should not be taking this long. Oh, okay. It was, for some reason, it was just hanging on plot. Let me go ahead and remove this so that that's not taking up some CPU. I'm hoping that everyone can still hear me, that this hasn't done weird things with my computer.
Yes.
Yeah, okay. Yeah, sorry about that. So we have, this is some German MRI data. This is from a recent language paper where we were interested in what are the velum kinematics for nasalization in vowels preceding N or nasal then voiceless obstruent versus voiced obstruent. So if anyone is familiar with Pam Bador's 2009 language paper, she had a very nice hypothesis about how vowel nasalization, what can be the sort of catalyst for vowel nasalization in certain contexts, is an aerodynamic constraint on the velum movement in these voiceless contexts. So we're using MRI data to test this for German. So here we have an example of a vowel followed by a nasal and a voiceless obstruent. And if we look at the dimensions for the images associated with that. Now, if you've never, so most of you, I'm assuming, have worked with at least two-dimensional matrices where the dimensions are in order of rows and then columns. You may or may not be familiar with three-dimensional matrices. Now, this third dimension is typically, there are different names for it, but typically they're referred to as pages. So here we have here 136 by 136 by 32. So this is 136 rows by 136 columns by 32 pages. So what we have here are the first two dimensions are the rows and columns of individual images. So we have square images here. We have the same number of rows as columns, and then there's a sequence of 32 images of that resolution. So we'll see some images here in a bit, but let's first listen to the audio for that's associated with these images.
Sonntag.
You should be able to hear that. That was all good. Did you hear that audio?
Yeah,
Yes.
all good.
Yeah, okay, cool. So we're comparing this to the second data set, and we can look at the dimensions here. So we have the same resolution, makes sense because it's from the same scanning session, but we have now two fewer images. We have 30 images here instead of 32 images. And if we listen to the audio here.
Sonntag.
So the idea behind this paper is we were looking at, in these contexts, does the fact that there is a voiceless versus a voiced obstruent following the nasal, does that constrain the timing and magnitude of the velum gesture and how that overlaps with the vowel? So we have images associated with these two contexts, and we're actually going to do some very similar analyses to what I did in that paper here for the workshop. So we listened to the audio, but let's go ahead and look at some of the pictures. Now, one of the things that working with pictures, working with images, I guess, in R is a little bit more difficult than a language like MATLAB for a couple of different reasons. MATLAB, for all of its, the issues that I may or may not have with MATLAB, one thing that it does very well is work with images, because images are matrices, and MATLAB is designed as a matrix language. So R is a little bit less easy to work with in that way. But the other thing is that if you're doing something like specifying a color space for plotting, very often you have to generate that color space yourself. So we're going to go ahead and do that and just create a sequence of numbers, of numeric values between 0 and 1 of 256 values along that scale. So we're using a function that we saw yesterday, the SEQ, the sequence function, to do the same kind of thing. We're creating 256 values. So this is an 8-bit space, 256 values between 0 and 1. And then we're creating, along that sequence, putting that into a gray color scale. So if we look at this, these are then hex values associated with that range of numbers. So now we have a color scale that we can then use to plot some of these images. So let's go ahead and just take a look at the first image in the first data set. Now, if you're not familiar with this kind of notation in R, so you're probably familiar with things like, I don't know, like if we say data 3, come back to the data 3, and then the audio, and we say, oh, just the first 100 samples, right? Now, this notation works because we only have one dimension, right? So this is a vector. So we can just simply say, give me the the first 100 elements of this vector. Now, if you want to specify a certain range within a dimension, but leave all of the other information intact, you use commas, and you leave that element blank. So if this were, for example, a two-dimensional array, which it's not, but let's say I want to say, give me the first 100 rows and all of the columns, then I can do something like this, right? Conversely, give me all of the rows for the first 100 columns. I can do something like this. So in MATLAB, we would have a colon. In R, you just leave that field blank, and that's basically saying, give me all of, right? So here, we're having blank, comma, 1. So this is saying, give me all of the rows and all of the columns for the first page. So essentially, give me all of the voxels in that two-dimensional array. Give me all of those voxels for the first image. And let's plot those on grayscale. So let me go ahead and adjust this so it's square as it should be. Okay. So here we have the first image from the MRI video for this data set. And we can, plot the second image, see how it moves. We can plot the third image. Okay. We can even do something like, so we've got, how many, it was 32. So we can say like for we've already done 3, but 4 to 32. Go ahead and just like, let's plot all of them, right? And now you can kind of like click through these and you've got a little movie, right? So you've got all of the images in time for the MRI. Okay? Now, again, the research goal here is there a difference in the Vellum kinematics? And primarily what we were interested in is the part of the Vellum kinematics that is associated with the anticipatory vowel nasalization. So does vowel nasalization begin earlier in the voiceless context? Is the magnitude higher or lower? Or we'll see what's going on in the vowel. And there are a number of ways that we can do this, right? So what we're trying to do is capture some time-varying information about the velum, right? So the velum is located here. And as we kind of click through, we can see there we've got a nasal. So the velum is opening and then it closes again. So we want to capture that movement, right? So the lower that the velum is, the more nasalized it is. And we want to get some indication about both the magnitude and the timing here. Now, there are two primary ways that we can go about this. One is top down, one is bottom up. And we're going to actually do two different approaches here for the two exercises I have planned. And what I mean by top down and bottom up is we can use our information as smart phoneticians about the vocal tract and about speech articulation to impose some sort of restrictions on the image and then get a measurement out of that and then interpret through our sort of like our lens of our top-down knowledge what that signal means. That's the first exercise we're going to do. The second exercise in the second half is going to be using principal components analysis to let the image variance tell us what the movement is, right? So that's sort of a bottom-up approach where you don't make you don't impose much on the analysis other than just specifying a region of interest. So let's start with this top-down approach. So we're going to take a top-down approach where we are going to specify a part of the image and say we're going to do an analysis here because this very particular part of the image means something to us phonetically. And what we're going to focus on here is not just the region of the velum, but very specifically what's called the velopharyngeal port. So that is the actual, that's the sphincter, the space that allows the air to go through the nasal cavity when the velum is lowered. Because this is a two-dimensional mid-sagittal slice, we don't actually have that whole area. What we have here is there's a gap in the image that is associated with that, right? So this bit here, so if you're not familiar with MRI, flesh shows up as varying degrees of gray, and air and bone are essentially black. So what's happening here is when the velum lowers, the fact that this is very dark here tells us that, again, with this top-down knowledge, we know that this is not bone. So this is going to be air, right? So this is an air or an available air column here that then is created when the velopharyngeal port opens. And then when it closes again, the pixels become brighter because flesh, the soft palate, is moving into the area where the velopharyngeal port is. So we're going to have a first analysis where we are outlining the velopharyngeal port, and then we're going to then create intensity metrics based off of that. So in other words, we know that when flesh moves into some voxel site, the pixels become brighter, or the voxel becomes brighter. And when it moves out of that site and there's air there, it becomes darker. So by taking the average sort of intensity in some region, that can then be interpreted then as velum movement. So one trick to do this, like if you have some sort of, you're comparing two articulatory states, in this case, velum up versus velum down, one way to do this is to simply find images that are representative images of those two states. And I've already, I've looked through and I picked some here for you. So the first one is going to be velum up, and the second one is going to be velum down. So if we look at these, so here we have velum up. This is the very first image in the word here. It was zonta, and then velum down. Okay, so we have these two images. We have velum up and velum down. Well, a really simple way to just figure out where the velopharyngeal port is on the image. So again, here, when the velum is up, then the soft palate is sort of filling in that space of the image where the velopharyngeal port would be if the velum were down. And here the velum is down, so that space is now open, so it's darker. Well, we can just simply take a difference image. We subtract one from the other. Now, this works out really well because then we have essentially sort of more or less random noise here that we can kind of see a face, but this is just from maybe just very slight movements. And where we see any variation from 50% gray, so anything brighter or darker than that, is movement that or displacement of the articulators in one image that is not in the other. Okay. So here, specifically because the first one is velum up and the second one is velum down, when we subtract one from the first one, what this means is that this bright area here, hopefully you can see my cursor, this bright area here is the velopharyngeal port. So in other words, this is a region where there was flesh in the first image, but not in the second image. So that's where we use our phonetician brains and we say, aha, that's the velopharyngeal port. I'm going to create a region of interest right there. And then I'm going to take some measurements. Now, here's where the bug occurs that I was talking about earlier. So currently, I have the text that is zoomed in for your benefit to view this here. Now, where we're going to be using basically throughout the rest of the day is a function in base R called Locator. Now, it's a really, really nice function that can be used in a lot of different ways. And all it really does is when you're using RStudio and you have a plot that's in a window here, all RStudio is sort of doing under the hood, anytime you have a session that's open, you make a plot, it is saving, I think, a PNG image in a temporary directory. And when you then move through the plots, it's just finding what that temporary image was. Now, the locator function will allow you, if you click on it, on that image, it will give you the coordinates of that image that is being displayed. And you can put a number in here. So if I say locator and I say, just say 1 here, what this will do is it will stop after I click 1 time and it will give the results. Now, let me show you the bug. I'm going to try to click as close to 0, 0 as possible. And here's the result. That is nowhere near 0, 0, right? It is far off in the X dimension. So this dimension here. And it is very, very far off in the Y dimension. Now, I think what's happening is I believe that RStudio, when you change the font size, what it's really doing is it's a scaling factor of the resolution that it is presenting to you. Because if you make this any smaller, I've already found this is the threshold, right? So if I go this small or smaller, now if I do the locator function again, and I try to click exactly on 0, 0, look at that. We get numbers that are very, very close to 0 and 0. What this means is that I'm going to be sort of flipping back and forth between the 2 different font sizes to get the correct coordinates. So that being said, the locator function, if you don't put in an argument for n here, if you just leave it open, it will allow you to click as many times as you want, wherever you want, okay? So I'm going to click here and here and here and here and here. Some of you, when you're done clicking, you can hit the stop button here. This doesn't work for me for some reason. I have to hit the escape button. When I hit escape, now I clicked 5 times. I have 5 X and Y coordinates. You can probably see where we're going with this. You can then make a region of interest of any number of points that you want in a polygon and then get those coordinates back. So using those coordinates, you can then use the polygon function to then create, as the name implies, a polygon to then plot on top of the image. So I just clicked wildly in, oh, I didn't save it to anything. Let me save it. And I'm gonna, I don't know, just click around the lips here. Click, 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 click. Hit escape. Now we have a polygon that is created around the lips. Now, if I zoom back in, you'll see how drastically this goes wrong. So let me try this again. Now let me try actually to click on the exact same points. I'm going to try to click here, and here, and here, and here, and here. Now, when I try to plot this, it's totally out. It's not even the same size. It's not the same location. It's just gone crazy. Okay. So apologize if you can't see the font very well, but I'm going to have to zoom out here. I'm going to go ahead and clear this. And we're going to try this again. Now, what I'm going to do then is use this to then create a very tight polygon, a region of interest, just at the velopharyngeal port. Okay, so really just these bright pixels here. So I'm going to do something like this. Really tight around. Okay. Now when I plot this, we've got a nice region of interest that is just confined to that space that we are using our top-down knowledge to interpret as the velopharyngeal port. So there are a number of things that we need to do then to create what's called a mask of the image. So both of the approaches that we're going to do here, and actually a lot of, if not most of the sort of approaches that you'll see in this kind of image analysis, is essentially defining some sort of region of interest and then only focusing on the voxels that are inside that region of interest. Well, what that means is that we're ignoring everything else. We're ignoring all of the other voxels that are outside of that region of interest. And so to do this, what we create is what's called a mask. So a mask is simply an object that is of the same size as the image, that is simply zeros and ones. So the mask will be zeros in all of this area outside of the region of interest, and then 1 for all of the voxel sites within that. If you then take that mask and you multiply it by all of the images, well, what that does is just zero out then everything that's not in there. So that's the idea of a mask, and this is going to, show up in really most types of image analysis of this sort. So there are a number of things that we need to do to create a mask in R. We have the polygon that we've plotted here from the coordinates, but what we need to do is to create a different type of polygon object specifically in the SP package, so short for spatial. So we're going to do that and then create a mask out of that. So polymask. So actually, we should even be able to view this. So polymask. Can I do that? Can I do? Can I do that? No, I can't. I can't do any of these things. I thought we could just actually plot the mask itself and we would have a bunch of black and then a little blob of white, but it looks like we can't do that. So what we're going to do is then apply that mask to all of the images. Now, this brings up another issue in working with images, not just in R, in any language, is what is the origin of the image? Okay. Now, let's go ahead and look at the documentation for the image function. So just in the base graphics here, we're going to scroll down to here. Now I can probably zoom back in. There we go. Okay. Notice that image, that the function that we're using here, image, interprets the Z matrix. So that's the intensity values here as a table of this function of X and Y, so that the X values correspond to row number and the Y axis to column number. So this is with column 1 at the bottom. So this is 90 degrees counterclockwise rotation from the conventional printed layout of a matrix. So we're used to, if we're dealing with a matrix, where's the first element? First row, first column is in the top left. But if we're plotting values in a plot, the origin, so the origin of the matrix is in the top left, but the origin of a plot is in the bottom left. So we have to do some flipping around here. There are different conventions for different backgrounds that assume one origin over the other. So I've done some painstaking things that you don't have to do and flipped things around in the right order in order to get the mask that on as it is appropriate. But let's go ahead and not do that. Let's view the incorrect masked image first. So what we're going to do is we first have to what's called rasterize the image. So currently the image is a matrix of values. So it's just just a data matrix. We have to turn that into essentially an image object. So that's what we're doing here. We're going to rasterize the first image, and then we're going to apply our mask to that. So we're going to take that rasterized image, put it in this mask function, applying the poly mask object that we have. And then we're going to turn that back to a matrix of numbers, because the image function assumes that you are inputting a data matrix to then turn into an image. So we're going back and forth here a bit, and then plotting that in grayscale. So what happens when we do this? Right, okay, so a couple of things. One, this doesn't look like a velum or even a velopharyngeal port, right? So if you can probably guess what this is actually the alveolar ridge right here. And if we think about where the region of interest is, you can see that it's been flipped, but it's not just flipped horizontally, right? So if we look at, this is the kind of like the pointy bit here, it's like, it's just rotated, right? So it's rotated again, 90 degrees, in this case, counterclockwise. So in order to get the correct coordinates in the data matrix that are associated with the mask, we need to flip some things around. So I've given you what you need to do to be able to do that here. So if we view this, this is the correct way. It is flipped around the correct way, and we're going to flip it back when we actually kind of view things. But you can see that this is where this looks more like this region of this differenced image, right? So now we've got some correct values in here. I personally, I know a lot of people don't like to do this, but I do embed functions in this way. If you are more of somebody who does piped functions, then this is the way to do this here. And this is the reason why we've loaded the Megret R, however you pronounce that, to be able to get this pipe function. So these are essentially doing the exact same thing. So we are first taking the image, we are transposing the image, which flips it around a diagonal. We're rasterizing it. We're flipping it along only one of the dimensions, then applying the mask and then converting it back to a matrix. So if we do all of that and then flip it back, now we have that velopharyngeal port in the correct location where we're used to seeing it in the image. Now, I realize that that's probably super confusing. That's not actually really that essential for the workshop here. This is just to highlight, you really need to understand what your data are, what the dimensions are, and also any assumptions that come along with those. So there are a lot of assumptions that come along with working with images. Different people who work on images and then create these packages may have different assumptions going into it. So you really need to do things like what we've done here by actually plotting the region of interest to ensure it is where you think it should be, and then also plotting the masking of that to make sure you're getting the values that you should be getting. Okay, so with all that being said, you have the code for doing that. So we have that code structure. We're going to go ahead and apply that now to all of the images, right? So if we took the average of all of these pixels that are here, the relative average compared to, all of the pixel values that could occur here is going to be pretty high because the velopharyngeal port is closed. The soft palate is sort of invading that space. So it's going to be relatively high. So that one value is we're going to interpret that as the velum is high. So you can see where we're going with this. We're going to get that average value, and we're going to do it for each of the 32 images. Then if we plot that signal over time, we should get something that's like a nice velum height function for a word that starts with an oral obstruent and then has a vowel and a nasal consonant and then has another oral obstruent. So the first thing we do is we're going to think about, okay, what is our end object going to be? It's going to be just a vector of numbers that is as long as how many images we have, because we're going to have one number for each image. So first, how many images do we have? Well, again, that's the number of pages, so the third dimension in our data structure. So we can just go ahead and make that a variable here, just 32. We're going to then pre-allocate a vector of 32 zeros. Well, here it's a Boolean vector, but they're zeros, right? We're just going to fill that. So for each of those spots, we're going to fill it with an average value. Okay. Now, this masked image, so we have all of the same dimensions of the original image, but all of this area here is blanked. So these are actually NA values, right? So the only real numeric values we have is everything that's inside the mask. So there's an easy way that we can get a number from this, is that when we apply the mask, we're going to take that image and we're simply going to take the average and remove all of the NA values. So that's just going to give us the average intensity for all of the voxels that are in here. Okay. Hopefully everyone should follow that logic. We're going to go ahead and run this really quick. And we're done already. And now, before we plot it, let's look at our vector again. Now we don't have falses, we have actual values for each of these. And if we plot this, lo and behold, that looks like what we would expect. Again, we're interpreting this as velum height because when there are voxels that have bright information, there are a lot of them in there, that means that the soft palate is in the velopharyngeal port area, so it's closed. So that should give us high values here. Then when the velopharyngeal port opens, this shoots down. Okay. And then you can do things like, find the point of the greatest nasalization, which is simply because we know how to interpret this. We say, which min MR dat, that's 18. We want to find the time point associated with that. Well, we take that's the number of samples. So the number of samples divided by the sampling rate. This is, well, 350, let's say 360 milliseconds after the start of the file is the point of maximum nasalization, for example. We can also do things like plot on top of this. I've included in the data structure Data1. So I have the word, I have the audio associated with that, I have the images, but then I also have some time points. So those are time points in seconds. Yep. Oh, no, why did I just summarize just one word there, or just one number? Yep. So time point in seconds. So we're going to take that time point in seconds, and just like yesterday, again, sampling rate is number of samples per second. So we're going to multiply the time point in seconds by the sampling rate. We're going to round that to the nearest whole sample, and we're going to add that as a vertical line here. So we're going to do that for the start of the vowel, plot that in blue, and then the end of the vowel, plot that in red. Okay. So this then, for that whole word, this highlights the region of the vowel. So we can see here, even in German, which is claimed to not really have anticipatory vowel nasalization, we can see here clear anticipatory vowel nasalization. Okay, I realized that was a lot, and I realized that there are probably questions before we move on. So I think this is a good time to take a break.
Could you explain the creation of the mask a bit more in detail, like the code?
Which parts? Can you?
The poly mask, where you the create mask.
This
yes.
one here?
Yeah.
So we're taking. Let's see. So if we break this up a little bit, let's see. So or SP polygons is a plural. Trying to think, so it's been a while since I've done this bit. So it's taking coordinates, but why did I make it a list? Probably because it gave me some sort of issue with it not being a list. So poly is currently, what is the class of poly? It is, right, so this is a sort of proprietary polygon object from the SP package. Now, if I were to, so if I take this, it will give me something. Okay, so it'll give me some information. Now, if I do this without making this a list, converting it to a list. Yeah, so it wants a list. So this is where I'm taking this object and creating a list out of it to put into here. Now, this is the same thing. For whatever reason, whoever wrote this package, it's not the objects that are created are not talking to each other well, because this is created from this package, but it's not a list. And it wants a list as an input to this function. And the output of this function doesn't create a list, but it wants a list for the input to this function. So basically, we're using the functions that are part of this, this package in an order that it needs and converting everything to lists. So so if we look at what is created here, these are the vertices of the polygon. Okay, so these coordinates here. But then we need to convert those to a spatial polygon. Oh, I don't know. It's been a while since I've worked with this. I'm not sure exactly why I needed to convert this, but I did need to convert this to actually mask the raster image. I'm not sure. I don't think I'll be able to actually walk through all of this right now. Why we're using one function and then another.
Okay. Well, thank you.
No worries. As the ROI is created and marked manually, would that have an impact on the results, like a finer versus coarser resolution of the region? Yeah, for sure. Is there an automatic way to identify the ROI? That's a really good question. That's actually closer to kind of the approach we're going to take in the second exercise using PCA. It's not an automatic way of identifying the ROI. It's not an automatic way of identifying which pixels in the ROI are actually contributing to the variance. So it's an indirect way of yes, saying these are the fine-grained pixel sites that we need to concentrate on, if that makes sense. There are ways of identifying what the ROI should be, but it really, all of this kind of image analysis is almost a bespoke thing. You have to know what is your research question, what is your data, and then that then defines what kind of approach that you can take. We're going to see some different ways of looking at the image variance in a way that is helpful for different types of research questions, which may also kind of answer your question a little bit, Raphael. Yeah, so that's a really good question. Is it mainly applicable to view peripheral port opening, also other stuff like tongue and jaw height? That's an excellent question. Certain bits of this are applicable, certain bits are not. You have to, here's where you really need to understand the data and also understand the speech articulators to know what is the correct thing you have to do. So the vela movement is fairly constrained, right? It's got one primary axis of articulatory movement, which is actually why I use PCA a lot to pick up on that axis. So something like this can work really well. Now, the tongue is in the complete opposite direction, right? It's got many different axes of variation and many different sort of articulatory degrees of freedom. Now, there are certain things that you can, there are concepts from this that you can use to sort of constrain certain parts of the tongue. Not physically constrain the tongue, but constrain the parts of the image that you are considering for certain articulatory aspects. So, for example, if you know you are interested in, for example, just tongue tip contact with the alveolar ridge, well, you can create an ROI that's going to be really similar to this. We can actually do this, and let's do this right now. So we're going to do the difference image again. Well, the difference image doesn't really matter here so much. I guess so. So we're interested in just this region right here. And same kind of thing where the tongue tip is moving in, we're going to have higher intensity. So we should, let's create a region of interest just around that. Oh, this is going to be totally wonky because I have to zoom back out. Now let's try this again. Yeah, so now we have just a region of interest that is really tightly constrained to that part of tongue contact. And we can make a prediction on what then the signal should look like. So this is zonta, right? So we should have a signal that starts high, goes low during the vowel, and then goes back high again, and then goes low for the schwa. So let's see if that's correct. That being said, maybe I'm totally wrong and I've messed things up. It should be fine. Let's go ahead and view that. That's the region that we want. We'll make our signal. Yep. So what that actually doesn't start high because we're not starting at, we've got a little bit of silence, and then it goes high for the tongue tip closure, it goes down for the vowel, goes back up for the alveolar closure again, goes back down for the alveolar or for the schwa. So that's a way of, you know, that there's a lot of different, you know, articulatory degrees of freedom here, and you are constraining that image space to only focus on one. Again, that is a top-down, you know, we know the action of the tongue tip that we are anticipating, and we know where that is going to be in the image. So we're going to use that top-down knowledge to define that region of interest. And then when we do that, we interpret through the lens of that steps of logic to then know what the signal means. But it's the same kind of idea, right? You can also use Locator instead of creating a polygon to create a line, and then you can do things like take the average along that line, or if you want to look at something like not velopharyngeal, or not like velum opening, but actually get a better estimate of the actual velopharyngeal port size, you can do things like, so we'll create, you know, if we create a line this way across the velopharyngeal port, then we could take all the pixels along that line and then find some threshold for pixel intensity, and then count how many pixels are below that threshold. So that then is an estimate of how many pixels there are corresponding to the actual velopharyngeal port. Multiply that by the resolution, and then you can get the actual spatial resolution of the MR image. Then you can get an estimate of the aperture, the actual aperture in millimeters, or millimeters squared in this case. But it's the same kind of idea, right? So that's what I mean by we're taking the same general concepts and applying it to different types of questions. Now, the second exercise, we're going to be doing much less of that, right? We are only going to be setting a region of interest that is much broader, and then letting the data tell us what the important information is. Right. Okay, so we're halfway through. How are everyone feeling? I think we're doing good on time. I'm fine to continue along right away. If we want, you know, a few minutes for a break, I'm also fine with that. I don't think we're as pressed for time as we were yesterday, because we don't have the introductory stuff, but we're basically halfway through the second part of the workshop.
I think maybe a couple minutes break would be cool.
Yeah, let's do that. So she come back at 5 after, so 4-minute break.
Sure, thanks.
Sound good? Okay. Stop my share. Actually, I'm gonna keep my share on to make sure nothing goes wrong, and just stop my video. Okay, cool.
Yeah, recording now.
All right, cool. Hopefully, I know that was really short, but hopefully that was at least a bit of a breather for everyone. Right, so like I said, there are these two main exercises we're going to do, but we are approaching the same problem. Our goal here is we want to get movement of the velum, and as I said at the beginning, we're going to do this in two different ways. One is top down, one is bottom up. We've just looked at the top down one, where we use our information about the vocal tract and about speech action to define what the region of interest is, which we are telling the algorithm what the important pixels are. For the second part, we are going to let an algorithm tell us what the important pixels are. To do that, we're going to use principal components analysis. But before we get to that, I also just kind of want to show these are some bits I've added in the code this morning that aren't in the tutorial that I thought would be nice to sort of just give you some options to think about in how you can kind of, you know, use the data in different ways. So if we come back to this original image, so this is the difference between two images. Now, that gives us some really cool information, especially for something like the velopharyngeal port, where it's got a very limited movement. So we can interpret flesh either there or not as something that's important. But there are other things that we can do with this stack of images to get other types of measures. Let's say if for some reason you wanted to get sort of like a baseline image to compare images to, and you wanted to ask the question, what is the average image across all of these? Well, here we can use the apply function in R. And it's a little bit confusing because if you look at the documentation for this, the second argument here is margin. And margin says a vector giving the subscripts which the function will be applied over. Now, I think that's super confusing because what it's really doing is, I think it's easier to understand it as which dimensions are you going to hold constant. So what we're going to do is to use apply on all of the images for the first word. We're going to hold constant the first two dimensions, which are the X and Y dimensions of the image, and we're going to apply the mean. What that means is that we're going to apply a mean over the two dimensions that we're holding constant across the third dimension. In other words, we're going to get an average image for all 32 images. So if we do that and then plot it, it's not super meaningful, but this is mathematically the average image for this word. Now, something that might be more useful to you is not doing just a difference between two images, but if we then sort of extend that logic and we want to look at what is the total variance across all the images, well, we can use this same logic here. Instead of the mean function, we apply the var function. Now here we have something that's probably a little bit more interesting. These are the regions of the image that, as we have just shown, we've applied the var function. So these are the pixel sites that have the most or the highest variance across the images. So these are just, a couple of different things that you might want to do. Or you can do things like look at the variance over time, or as I've given here, applying Euclidean distance function. So we can compare to a reference image all of the individual images for Euclidean distance of all of the pixels. And instead of holding the first and second dimensions constant, we're going to hold the third dimension constant. What this gives us then is it's going to calculate it over those first two dimensions and give us then a time varying signal. So here we can do something like plot this. So this is the Euclidean difference. So this is how different from the average image is all of these images over time. We can use any image we want, so we can even do things like, we know that this is our nasal image that we've chosen as a referent here. So we can do something like this. Plot this. So this tells us, well, what does this tell us? This is 0. So this is the image that we chose, right? So this is exactly 0 because there is no distance between the two of them. But this is interesting because we can get sort of a different type of interpretation of co-articulation here, I guess, in a way. So this is not just co-articulation of the velum. This is sort of, I guess, co-articulation of the entire vocal tract. So we can do really interesting things here, like when we compare to some specific point in time, we can look at the time profile for how do all of the articulators work together to time towards that, or something like that, right? There are many different ways that you can sort of like think about this and kind of have brainstorms on how you can use these things, and then importantly how to interpret them. But I just wanted to give you some other sort of like little tricks here that you can use to sort of make full advantage of the image set. But for the PCA, we're going to use that same difference image. But here, instead of just making a region of interest over the velar pharyngeal port, what we're going to do instead is make a region of interest over that encapsulates the entire bounds of the velum movement. So that's going to be not just the white here, but the white and the dark. So between those two images of velum up and velum down, we want to capture a region of interest that then will mask out everything but the whole region of velum movement. So we're going to make it quite a bit wider. We don't want to capture too much because we don't want to get tongue movement in here, but we're going to do something like, I don't know, like this. I don't know, something like that. So if we plot that, now we have, we still have constrained a region of interest, but we have far less constraint on it. What we really are wanting to do is just capture the entire region that the velum can move in the image. Because what we're going to do then is take those pixels, make a vector out of those pixels, then create a matrix of those where we stack those vectors together. So every row in the matrix will be a new vectorized image. And then every row is a separate image. So each dimension is then a voxel site and each row is a separate image. When we submit that to a PCA, then we will get some pretty cool results here. So important thing when doing PCA. So this is what we're going to do here is more or less the exact analysis that I did for this language paper. I happen to do that in MATLAB instead of R, but the technique that we're using here is the exact same thing. This is something that I do a lot. I've used PCA for ultrasound and I use it for MRI, and it works really, really well for certain number of research questions. But something, if you haven't used PCA in this way, what you really need to remember is you need to have, so first of all, you have to have a separate PCA model for ideally for, I mean, depends on your research question. For something like this, you have to have a separate PCA model for each speaker. The reason is that there's a lot of, for example, morphological structural variation across speakers that we want to ask the question, what is the important variance for this speaker? Conversely, we only want one PCA model per speaker. The reason for this is that we don't want to combine. So what we could do is one PCA model for the first word, and a second PCA model for the second word. But there you're comparing apples to oranges. So what PCA does is it's a linear combination of these individual dimensions. So that linear combination is to be different for potentially each model that you build, even if you're using the same images from the same scanning session. So we really want to compare apples to apples. So we have to have one PCA model that is then combining the data from both of these words. Okay, so that's really, really crucial when you're doing something like this, is that you have to combine all images into one matrix. So that's the first thing we're going to do is we're going to create a new field here called combine, and we're simply going to combine the images from the two. So here, what we're doing is pre-allocating an array that has the same, well, actually, we're not pre-allocating, we're actually filling it. So we're taking the images from the first set, combining that with the images from the second set, and we're forcing it to have the dimensions that we want. So it has to have the same image resolution, And then the third dimension is going to be as long as the sum of the third dimensions for the two data sets. Hopefully that makes sense. We go ahead and do that. Boom, it's already done. And then if we look at the dimensions here, we have, if we look at all the dimensions here, now we have a 136 by 136, so the same image resolution, but now by 62, okay? So we're going to take that 62 and make that into a variable image num, so that's 62. And if we compare that then to the number of images separately for those two, those are 32 and 30, so that's great. We've got the right number here. Okay. We're going to do the same thing that we did before. We're going to make a mask out of this polygon that I have highlighted in red. Now, a couple of things that we need to do here. The first thing is I want to see how many voxel sites there are within this ROI. Okay. So what I'm going to do here is simply apply the mask and then take the sum of all of the pixels that, remember, once the mask is applied, all of the pixels outside of the mask are NA values. So I'm going to take the sum of all of the ones that are not NA. So we have 623 voxel sites that are in here. Okay. Now, we're going to see why this is a bit of a problem. Okay, so if we now pre-allocate a matrix for the PCA, we're going to fill it with NA values. It's going to have, again, so a PCA has to take a two-dimensional matrix. And the composition of that matrix has to be, the columns are your individual dimensions, the rows are your individual observations. And the observations in this case are separate image frames. The dimensions are voxel sites. Okay, so we're going to pre-allocate a matrix that has the number of rows equal to the number of images, the number of columns equal to the number of voxel sites. And what we can do then is, as I said before, we have to vectorize this. So what I mean by that is all of these pixels exist in two-dimensional space, and it's not even in a rectangle, right? We have it in a polygon. Well, we have to make a single vector out of that, so a one-dimensional array, because that's the only way that we can then fit that into a two-dimensional array by adding all of them together for the different images to then submit that to PCA. So we have to vectorize that, all of the pixels that are in there. Now, this is a bit of a problem. So when we do this, and then look at the dimensions here, to have a good PCA model, you need to have ideally fewer dimensions than observations, but at least the same number or fewer. We have 10 times as many dimensions as we have observations. PCA isn't going to work here. And actually, I'm going to reset this a little bit because I have the code set up for 10, and that's just easy to think about. So I want this actually a little bit less than 10 times. So I'm actually going to just go ahead and reset this ROI with just a slightly smaller region. So that's fine. Yeah, so we're still capturing. I had a bunch of blank space up here that we don't really care about. So now we don't have that. So this is all fine. It's going to be the same. Create that. So the number of voxels now should be much smaller. Good, 502. Okay, so now if we do the same thing, and we have less than 10 times as many, which is what we want. Because what we're going to do is we're going to downsize this image. So in other words, we're going to make the resolution smaller. So in a real experiment, or if you were really doing this for a full study, you wouldn't necessarily have to do this. Or if you did, you wouldn't have to do it as as sort of heavy-handed as 10 times downsizing, because you're going to have many more images. This is still a good thing to do because, one, it turns out with PCA that you can downsize the images pretty heavily and it really doesn't affect the results. But also, it's going to lessen your computation time considerably by downsizing your images. So it's a good thing to have in here. Here, we need to do it to have a well-formed matrix, but it's also a good thing to have in mind for your real practice. So what we're going to do is we're going to say, all right, we're going to take this image resolution. We're going to downsize it, or decrease the resolution by a factor of 10. So we're going to now pre-allocate a matrix for the PCA model that's going to have the same. Again, we're not changing the number of images, so it's going to have the same number of observations. So in this case, same number of rows. But instead of the same number of columns, or the number of columns equal to the number of voxels, it's going to be the number of voxels divided by our downsizing factor here. So if we look at this now we're okay. We have fewer dimensions than we have observations. So we have 50 dimensions and we have 62 observations. So now we can we can do a PCA on this. So what we have to do then is we can't submit the images as is. We have to resample them. This is, I'm going to show you kind of what we're dealing with here. Before I do this loop, I'm first going to just look at the first image. So the first one here is going to be 1. So what have we done in vectorizing the image? So that may or may not make sense to you, but see how we have all of these different voxels that are inside this sort of wacky shape here. Well, by vectorizing, we're taking all of those and basically stringing them out into one line. So if we plot this, that then it looks kind of crazy, right? But it looks crazy because it's wrapping around. So it's like starting here and going, okay, take all of those, then take all of those, then take all of those, then take all of those, and take all of those, and go through, right? So we got this kind of wacky looking thing here, but now we have a one-dimensional object. This is a vector. We're going to resample this. So we're going to downsample this by our the factor that we have of 10. Now, if we plot new frame, this may look like we totally destroyed this, but this ends up being very usable for the PCA because the main patterns of movement that are going to be in here, we're still going to pick up in here. So we're going to then take that and then add this into the PCA. So let's go ahead and do that. So now let's take a look at this. Actually, so here we have the values here are voxel intensities. The rows are all of our individual frames for the two words. So we've got 62 MR frames here. And then the columns are pixel sites. Now, by vectorizing the image with the same mask, those pixel sites, wherever they may be located on here, are going to be the same for every image. What this means is that when we submit this to the PCA, it will analyze the variance across all of these dimensions, and all of those dimensions are in the same location in the image for all of the images. So let's go ahead and just submit this to a PCA, and PCA is super fast because it's basically a bunch of linear regression. We look at the summary here. So this is slightly less than the coordinates that I actually used in the tutorial, but very, very close. The first component here, PC1. So we've got so 502 original dimensions, and after we have the downsizing, we have now 50 dimensions across 62 images. There is one underlying component, PC1, that accounts for nearly 80%, so the vast majority of all of the variance in this huge matrix here. Okay. Now, because the velum doesn't have many articulatory degrees of freedom, unlike the tongue, so the velum moves up and down, doesn't move sideways, it doesn't go in and out, it doesn't go up, and it just does this, right? So I've done this for many speakers over the years, and by doing this approach, PC1 is always velum movement. Now, PCA is somewhat arbitrary in the sign of the PC scores, so you do have to keep in mind, we'll make a plot here and see what the sign turns out to be. But if we plot those scores from that PCA model, so but there are a couple of different ways of doing PCA in R. I'm using the base function per comp. And from that model, then the scores are under what's called X. No, PCA mod. There we go. So rotation, this is a rotation matrix. These are the PCA loadings, or the PC coefficients, but X is the scores. So we're going to plot the scores for just that first PC. And look at that. So remember what we have we've combined the images from two different words, both of which have nasals in them. And then we've done one PCA on those combined images. And then all we're doing is plotting the scores from the first PC, which accounts for 78% of the variance. And this is very easily interpretable. It actually turned out to be the case that the sign of the scores happens to match what I showed in the tutorial. So this is velum height. So starts high, goes low for the nasal, goes back up again. You see this little break here? This is in fact where we concatenated the two words together. So then we have a similar pattern for the second word. Starts high, goes low for the nasal, goes back up. What I mean by the signs are arbitrary is that this could have just as easily have been flipped, so that it starts low, goes high for the nasal, comes back low. So when you're comparing your speakers for something like this, you always need to check what the sign is here, and you may need to flip it depending on whether you want to interpret all of your scores as velum height in this case, or as the case I did in the language paper, not velum height, but degree of nasalization. So here we wanted to flip it such that as it goes up, that is essentially velum going down. So it's an increase in nasalization. But in any case, that's something that you need to be aware of. There are ways that is far too well beyond this workshop of taking those PC loadings. So not the X here, but the rotation matrix. You can take those PC loadings, map them back onto the original location of the image, and you can visualize what then the range of that PC1 dimension is. And it's going to look actually something, the loadings will look something similar to this, where, well, in this case, because actually will look, yeah, it will look very similar to this, because the high scores we're interpreting as velum height, as so the velum is up. So positive loadings will be where the velum is up. Negative loadings, so dark here, will be where the velum is down. So the loadings would actually end up looking very, very similar to this. I have a link to some MATLAB code in one of my GitHub repositories. If you want to see how I do that for something like this, sort of reconstitute the visual space of the PC loadings, you can look through that code there. We're not going to do that here, but one thing that we are going to do is take these values, we're going to scale them. Now, we only have one speaker here, but I'm including this step because you would want to do something like this if you have multiple speakers to compare across them. So we're doing simply min-max scaling here. We're adding this then into a new sort of just a velum signal, I'm calling here. So now we can interpret the y dimension as proportional velum height, right? So the closer to 1 you get, the higher the velum is. The closer to 0 you get, the lower the velum is. For the entire range that the speaker has in the recording. In this case, only 2 words, but you would do this over the whole recording. Okay, we're going to do a few more things here, but I want to take another pause, see if there are any questions. I know that was a lot that I just threw at you. So before we do things that are not related to the PCA specifically, I want to pause and see if there are any questions about that.
I would have a question on the scores and the sign of the score, because I did exactly what you did, and my image now is exactly flipped.
It's exactly flipped. Yep.
So that is what you just described, right?
Yes, exactly. Yeah. So they are. That's sort of the what I'm calling the arbitrariness of PCA.
Yes.
It's not totally arbitrary, but we can sort of we can interpret it that way. So the PCA is, again, so what it is a linear combination of all of your dimensions. What that means is that there will be some weighting applied to how you combine all of those dimensions together to get an individual component. So their first dimension, which is going to be some pixel site, is going to be either positively or negatively correlated with it, and it's going to have some magnitude associated with that. Those are the PC loadings and the scores are telling us how the original dimensions are related to the PC scores. What is the sign of that? So is it positively or negatively correlated with it? And what is the magnitude of that? So if you take, we can reconstruct exactly all of our original data by, it ends up being, I think, mainly multiplying, getting products plus some offset of the PC scores and the coefficients to get back to the original data. So we're basically just rotating the data. But when you do that, it doesn't matter whether it's positively or negatively correlated with the coefficients, because your coefficients, because your signal is flipped, your coefficients will then also be flipped. So instead of, so my coefficients here, I'm saying I'm going to have positive, so bright pixels here, they're going to be positive loadings here and negative loadings here. Yours will be this precise opposite. It will be positive loadings here and negative loadings here. so that's what I mean by it doesn't, they're the same thing. It's just that dimension of movement is what is important. There are individual pixel sites that will contribute to that dimension more or less strongly. Whether this is, you know, whether it's the velum up or the velum down, that is the like the way the dimension points, it doesn't matter, right? But because your scores are flipped from mine, your coefficients will also be exactly flipped from mine.
All right, thank you.
Mm-hmm. Any other questions? This is something
Chris.
that, yeah, so sorry, yeah.
No, sorry, please. Just I'll say something later.
Okay, yeah, I was just going to say that this ends up being I think, a really, really nice tool in these sort of image analysis techniques for different reasons. One, you could do something like we've done here, where we have an articulator that only has essentially one articulatory degree of freedom, so we can directly interpret the scores from the first PC. The other nice thing about this, though, is by definition, so the dimensions from the PCA rotation are what's called orthogonal. They're orthogonal dimensions, which means they are statistically not correlated with each other, right? So if I plot if I plot PCA PCA mod X, the first scores, I plot those against the scores for PCA2, and I look at the correlation for these. There is there's no correlation, right? No correlation. Now, same thing with 2 and 3, no correlation. 2 and 10, no correlation. 5 and 10, it doesn't matter. None of these dimensions are correlated with each other. What that means is what PCA does is it decorrelates your data. So all of these pixel sites are going to be very strongly correlated with each other. So individual pixel sites, when this large velum mass moves through them, there are going to be pixel sites next to each other that are all going to turn bright at the same time, and conversely, all turn dark at the same time. They're going to be correlated with each other. What that means is that you cannot, for example, take those pixels and use them as predictors for some other type of model, like a linear discriminant analysis, okay? You can use PCs because there is no multicollinearity in the data. So you can use those PC scores as predictors in subsequent statistical modeling, which is how I use PCA for image analysis most of the time. Most of the time, I actually don't use it in the way that we're doing here. I most recently used it in the language paper in the way that we're doing here, so I wanted to show you this. But most of the time, I use PCA in image analysis to decorrelate the dimensions to then use them as predictors. It's a really, really nice aspect of PCA. Is the meaning and interpretation of PC always straightforward? No, it's actually very rarely the case that it is straightforward. It's only straightforward here because we have, again, an articulator that only has one sort of axis of movement. And this is why, so like, what I was just saying in using the PC scores as then predictors for something like just even standard linear modeling or an LDA or, what have you, or cluster analysis, cluster analysis doesn't matter because they don't need to be decorrelated, but something where you're using them as predictors and the model assumes that there's no correlation between your independent variables, like most statistical models, then it doesn't really matter how you interpret them. You're just using it, this is just a tool to decorrelate the data. Here, we're using it as a tool to actually directly interpret one of the scores, but we can only do that because we know that this articulator doesn't have multiple degrees of freedom. Now, you could do PCA on a wider part of the vocal tract to identify what the degrees of freedom are. That's what the components will tell you. But you always have to interpret the scores in light of the coefficients, if that makes sense. So here we're not doing it because it's really straightforward. We know what it is. But if you had anything that's a little more complicated than this, you can only interpret what the PC score is in terms of articulatory movements by mapping on the PC coefficients onto the vocal tract. If in the ROI there are more than one factors, is this possible that may contribute to the differences in the image? How can we interpret the meaning of the principal component then? Yeah, so that's exactly what I was talking about. Is like, so you could, it's actually plausible that you could get some PC loading, like a PC loading set that looks like what I've shown here. And that is almost completely uninterpretable, because what that means is that the PC is a combination of velum movement and tongue body movement and lip movement, right? But maybe that's actually appropriate for your research question, because if you want to look at the coordination of articulators, well, then you would want to have potentially a larger region of interest to then look at which are the articulators that do move together that then contribute to the variance, right? So if you have a certain case where the tongue is always moving along with the velum, well, those are going to then contribute strongly to the PC scores of some dimension. That is going to explain a lot of the variance in your data. So you always have to keep in mind what your research question and what your data are to know what kind of method you might want to use. It is far less interpretable than, for example, what we did prior, which is just the velopharyngeal port. But what's nice about this is here we're not making any assumptions. Here we're letting the data speak for us, and we're doing it in a way that you can be more certain of comparing across speakers. So let's say you're doing a velopharyngeal port analysis, and you have different annotators that are, setting the region of interest for different speakers. Well, you have to then have some protocol. How do we define exactly what the velopharyngeal port is? Where is it in the image? Like, how do we're saying that this is kind of nicely shown here, but do we include this bit? Do we exclude this bit? Right? These are all decisions you have to make, and those decisions might differ between different people. Something like this, where you're letting the data speak for you, you can be much more sort of liberal with your region of interest, and then simply take the first PC score, check what the sign is, flip it if you need, scale it, and be done. And that's exactly what I did for the language paper. That's exactly the steps that I took for that. All right, let's go ahead and continue on. There are a few other things I want to show you, and then we'll still have time for questions after. So if we come back to this last, I guess no, not the last one, but let's look at the bottom again. So we've got these two velum height signals that are concatenated from two different words. Well, that only gets us part way. If we want to compare, again, we want to compare, is there a difference in the velum kinematics for one word versus the other? Well, again, we're really interested in the vowel. So that was what we were primarily interested in for this paper. So we need to compare where the vowel is in this first word to where the vowel is in the second word. But because we've concatenated them together, we have to be aware of, we need an offset. So this first word does start from the first sample. The second word doesn't start from the first sample. It starts from this sample here. So our offset is simply going to be the number of images in the first data set plus 1. That's going to be the starting sample for the second word. Okay. So that's what we've got here. The number of images in the first data set plus 1. We're going to divide that by the sampling rate. That gives us a time point in seconds for when the second word starts here. We're going to then add these to we're going to make a new sort of a new field here in the list of the starting point in seconds for the first word, which we already have, then the starting point in seconds for the second word plus this offset. So do that for the starting points, do that for the ending points. Now, if we, well, we've already plotted that. If we now then plot, we're going to plot just a dashed line that's going to be directly between the two, which is directly at the offset. That's here. And we're going to add on in blue the starting points of the vowels, in red the endpoints of the vowels, and then you can see where you could create a plot that's like in the tutorial documents of normalizing the time. So if we think about this, we're kind of bringing everything together we've seen over the 2 days. So this very end plot that I have here, you would do a number of things, right? You would normalize the time using this SEQ, that sequence function that we already saw, because these are potentially, they're going to have a different number of data points. We've already seen how to do that. Then plot them on the same plot using proportional height. And now we can start to actually see we've got a real result for an analysis kind of brewing here. So we can see that because this is, well, I've labeled this as degree of anticipatory vowel nasalization, but really is interpreted as how we have on the left here, proportional velum height. So from just these 2 words, mind you, we just have these 2 words, but this suggests that the degree of nasalization is greater before the voiced consonant, the voiced obstruent here, and that is somehow reduced before the voiceless. That is in fact in line with Pam Bador's 2009 proposal. And I have a link here to our paper if you want to read, if this holds out for the rest of our German speakers. So I think that's actually that's all I have. That's all I have planned. So we've got the rest of the time for questions if you want.
Great. So first of all, thank you very much, Chris, for this 2 days. It was extremely interesting. It's really nice to have, you know, like you said, like have the script, have the HTML, and this explanation of everything, which at least for me, again, like I rarely work with this kind of data, so for me it was quite a lot. But again, it's great to have all of this material available and kind of be able to come back later. So and your explanation was absolutely clear. So thank you for that.
Awesome. Yeah, and just to remind everyone, that HTML document, because the data is in my Dropbox, if you find this useful and if you want to share it with anyone, you can just share that HTML document, and then people can go through the tutorial and have access to the data on their own.
Yes, absolutely. And then this recording will also be posted somewhere. Everybody will receive an email, and then you know, if you find the recording, there will also be instructions there on how to get hold of the HTML file. So if you kind of go back and just have the recording but don't have the file anymore, there will be instructions to get that. I just wanted to say something quickly before or while everybody thinks of questions. Just because I know some people might have to leave early, I'll post some links in the chat, and some of those links are from yesterday. So you have links to the workshop page if you want to see what's happening next, and Slack. But also, if you could, you know, as you know, this workshop was free for everybody attending, and so that, you know, we can have more and more of these free workshops, it would be great if you could fill in this Google form to just give a little bit of, you know, feedback. It shouldn't take more than a couple of minutes, 3 minutes, and, you know, it's something that we can have, and we can, you know, go to the constants in the institution and kind of say, like, look how good this is doing. Can we keep doing more of these? So if you enjoyed taking part, and you know, and this will allow us to keep this workshop free going on in the future as well. So just wanted to point that out before some people might be leaving a little bit earlier. But now I'm again giving the floor back to you and to the questions about anything that we've seen in these couple of days, I assume, right? Because it's being the end, it's good to bring back some questions.
Where did I, so it depends on the data. So the time points, I have to remember. So it was for this project. So this is a project that I worked on when I was in Munich. The data, I think they originally were probably in prod, but then were given to me in MATLAB, and I just took the time points from there. I actually prepared the rest of the data, like the images, the EMMA data, the EMG data that we saw yesterday. All of those I actually prepared in R. So I read the images in, stacked them together in a list there. The audio files and the EMMA data, well, the audio files and the EMG files are WAV files, so I just read those in, and then, you know, put them into the list here. The EMG were CSV files, so I read them in like regular CSV files. So yeah, did all of that preparation just in R. Any other questions?
And feel free to unmute yourself as well if you don't want to write the question in the chat. You can just speak out.
Again, I want to highlight that so some of the stuff, especially yesterday, was kind of you know, that the first exercise is just they're really basic but kind of bread and butter things, you know, aligning two different signals with two different sampling rates, super important, but maybe not like, you know, that's not going to be the bulk of your analysis or anything. But stuff like spectral subtraction that we did yesterday, absolutely. That's used for denoising audio or Wi-Fi signals or lots of different things. That's a real thing that is used as a DSP technique. Everything that we've seen here today with the MRI, absolutely real methods that we use all the time. So this is, you know, this isn't all just like intro, you know, you'll never use this. This is real, like what I think is cool stuff that you can just take from here and do your own analysis with. I'm curious to know, I guess there are no questions. Because I know that this is probably a different style of a workshop, like giving all of the bulk of the material beforehand, and then you have to kind of read through it, and then we go through it together at a lightning fast pace. Does that format of this kind of material, does that work? Is it too fast? Is it too much? Is it right? Is it too slow? I'm kind of trying to still kind of figure that out myself. Cool, awesome, that's good to know. Because I think that that's, it's only 4 hours, which is, I mean, it's a lot of time to, to spend together, but really, if you think about it, it's not much time at all. And I think that this is a way to hopefully get you as much as possible in a way that you can remember it and then come back to the document later and understand all of it now better. Cool.
Yes, absolutely, I concur. And I think the HTML also kind of just works by itself, right? In a way that you can just work through it, and then you can take the Zoom part almost as a sort of question and answer or clarification. I think somebody was pointing that out. So absolutely, I think that that works so much well, and also it allows to. I find like the problem of doing everything without material in advance is that you always kind of have to introduce some of the basic aspects or spend more time, and so you end up having 20 different workshops where half an hour is almost like always overlapping of how do we get this thing in R, or how do I load this, and when that can be sorted out before, and then exactly like use this Zoom as more a clarification. So I think that definitely worked great.
Yeah. So I appreciate everyone doing I guess the homework ahead of time. So you probably got much more out of it that way.
Brilliant. I think that if we don't have any more questions, I mean, this is it's it. We're basically at 4 now. So again, thank you very much, Chris, for these couple of days. It was absolutely great, and we're very happy that you decided to join this series. And we're hoping to see you join future workshops. That we have such a variety of things lined up. I think that it's very exciting to have things like, even like I'm saying, like today is not something that I would generally use because of what I do, but I still learn things that I can kind of tweak and then reuse for different things, or kind of just it's just good practice and learning more R and coding, and so definitely that. And yes, and
I know, and it's R without tidyverse. Imagine that. You can use base R for things.
Yes, I admit I tend to overlook that too often nowadays as well. So, but definitely that is something. Okay, well, thank you everyone for joining. And again, I'm seeing that some people are already filling in the survey, and that's great. So next week, so I can't upload the recordings this week because I'm away and it will not let me do it. My VPN is not doing great, but so next week I will be uploading recordings, and then I will send those along to everybody who was to everyone who was what's the word, not just registered to this event. And then yes, I will also send again links and surveys. So if you don't do it now, you can do it later, and material and so on. And if you are on Slack, you will then be updated about future events and so on. So that's it. Thank you again, Chris, and thanks everybody for joining. I hope that you enjoy the workshop, and I will see you at the next one, which is I don't remember the exact date, but I think it's 20 something of September. So it's again a 2-day format. So it's I believe 22nd, 23rd, or 26th and 27th, that week of September, and it's all on the website. So we will see you there. Thank you.
Cool. Thanks, everyone. Bye.
Thanks. Bye.
Bye.